science with all of the section about the sun. We're going to cover all of the sun in one video here, so let's get to it. So first off, start with the structure and composition, and the only reason we know anything about the sun is from two things: direct observation, obviously, and the calculations about the interior based upon the behavior of our sun and other stars as well. So there are three outermost layers, the layers we're probably the most familiar with. The first is the photosphere, which is the visible surface of the sun. And I have an image here to kind of show that. So here we have the photosphere, right, is the visible surface of the sun. Okay. This comes from the Greek word photos, which means light, which makes a little bit of sense. It is a very hot and opaque gas layer with temperatures that are around 5,800 Kelvin or 10,000 degrees Fahrenheit. The photosphere radiates a lot of the energy into space. That energy, of course, well, not of course, if you don't know, but it comes from the core, which we'll talk about later. The photosphere is 500 kilometers thick, which sounds like a lot, but the sun's quite big. It's actually less than 0.1% of the sun's radius. But the proportionally small nature of the photosphere is why the sun seems to have this well-defined edge, because it almost looks like a cutoff in a way, right? It's like a crust in that sense, right? And the limb is this apparent edge of the sun's disk, and it actually appears darker than the center, which is a process known as limb darkening. And that is due to kind of our perspective of the sun, and that there are higher, cooler regions of the photosphere in those areas around the edge, right, or what we perceive as the edge, right, which are making it look darker, right? So we're looking at this spherical object, right, and it's got the same kind of uniform heat around it for the most part. But as we're looking at the edges, right, the edges are curving away from us, and so we're seeing more of the photosphere, right? We're seeing kind of that higher edge of it as well, right, which shows a darker, cooler region. Okay, next up is a chromosphere. The chromosphere is a thin, transparent layer above the photosphere. Let's see if I can actually get back to it. There we go. The chromosphere is a thin, transparent, it's almost the halo kind of looking thing in this picture, right? It is about 10,000 kilometers or 6,000 miles long or big, which is much bigger than the photosphere. It comes from the Greek word chroma, which means color. Normally, the chromosphere is only visible during a total eclipse, and it goes red at this time. Which is why during a total eclipse, the sun will appear red, is because the chromosphere appears red due to the amount of hydrogen gas it contains. And as you move outwards through the chromosphere, the temperature actually gets hotter. I don't know if they ever explained that. I'm not exactly sure why, but it will reach a temperature of 20,000 degrees Kelvin, which is much hotter than the photosphere. Okay, the last of the outer layers is the corona, which is the outermost atmosphere of the sun above the chromosphere, and it's from the Latin word crown. So it's kind of the crown of the sun. So you can kind of see the corona, this kind of hazy section right here, which is very, very prominent during total eclipses. In fact, I think it's the main thing we see in total eclipses, right? Let's see if we can get a picture of that up. Okay. Nope. Yep. There we go. So this is probably a better version of looking at the corona, right? So this whole outside thing right here is the corona, right? So you'll see the chromosphere right here. It'll turn red, right, when we see it like that at a certain point, right? But the corona, what it is, it's a bunch of rarefied hot gas that extends millions of kilometers into space, up to 3 million kilometers in the outer part of the corona. It's also, excuse me, I'm so sorry, extends millions of kilometers, but the temperature goes to 3 million Kelvin, which is incredibly hot. And so because of this high temperature, the corona will emit high frequency radiation, usually in the form of X-rays. Right, and if you guys remember, right, if we go back to our emission spectra, right, the hotter something gets, the higher up the kind of the electromagnetic spectrum it will radiate. And again, during a total eclipse of the sun, it's visible as a jagged white halo. And so when we get to the interior is within the photosphere. And of course, we've never seen the interior. So astronomers will conduct models that fit the data from indirect observation of the interior. And what we see is that the sun's temperature and density will increase as we go into the surface, right? Deeper and deeper in, it gets hotter and more dense. And at some point, it gets to 15 million Kelvin and 200 billion Earth atmospheres, which is insane. And the density rises to over 100 times that of liquid. No known element in the periodic table of elements can exist in a solid or liquid state in these high solar temperatures, which is why then that the sun is composed of hot gases. The sun's temperature is so great that the electrons are constantly separating from atoms, right? So we talked recently, right? We talked about how, the way electrons move up energy levels is by absorbing energy either through heat or light. And so the temperature is so hot that these electrons aren't even sticking with the nucleus. They are just shooting all over the place. And so these when these electrons separate, right, again, we have ions created, which ions means there's either a negative or more protons and electrons or more electrons and protons. So we're seeing the type that has more protons than electrons. And so we see a gas of ions called plasma within the sun. And so the most interior region of the sun is the core, which is where all the good stuff happens. As you can see here, this is the artist's rendition of the core. It is the power plant where nuclear fusion occurs, nuclear fusion being the thing that makes suns work. And the energy coming from the core provides heat and enough pressure to balance the inward pull of gravity, right? So the gravitational power of the sun is trying to pull the sun inwards at all times, but the energy that is created by the core is pushing against that pressure enough that it doesn't kind of collapse in on itself, which is what happens when we talk about black holes, which we'll talk about in a later video. So energy from the core then goes outwards through the interior layers. In the radiation zone, which is the next zone, light is absorbed from the core and then re-emitted at lower energy levels, right? So here we can see the radiation zone. Okay. So it takes energy from the core, re-radiates it at lower energy levels, which also corresponds to the idea that it's not necessarily the same color or kind of the white hot look of the center of the sun, right? Instead, it's kind of this lighter color, right? Which makes sense because it's at lower energy levels. And then we have these currents of gas in the convection zone that transfers most of the energy that's being absorbed from the radiation zone to the outer layers as heat. Okay, so if we could take a look at that over here, right? So then we have this convection zone, and these are I've seen pictures of this where it's just like kind of a bunch of circles, right? So we see like it's convecting gas, right? And then it takes it gets a lot of the energy the energy from the radiative zone, convects it up, and then shoots a lot of it out to the photosphere. I shouldn't say a lot, actually. It's not that much. But then light that reaches the photosphere escapes into space, right, from the convection zone. And it can take hundreds of thousands of years for energy from the core to reach the surface. So the sun rotates just like the Earth, west to east. However, it does not rotate like the Earth in that it does not rotate as a solid body. The rate of rotation varies by the latitude, where the period of rotation is shortest, obviously at the equator, 25 days. It's much longer at middle latitudes and slowest at the poles. I shouldn't say it's obvious at the sun's equator because the equator is the largest area, right? But it's slowest rotating at the poles, right? And so this rotation pattern actually likely contributes to the violent activity on the sun, because just the way that it's kind of making all the energy interact is inconsistent in a way, right? It's not moving all at the same time. So then you're seeing just all of these different atoms and molecules and energy interacting constantly, right? Because of these different periods of rotation, which is again why they believe the violent activity of the sun, which we'll talk about here in a bit, occurs. So now we need to talk about the nebular theory. Created by German philosopher Immanuel Kant, which, if you know anything about Immanuel Kant, this is not what he's known for at all. He's very much a philosopher of like existence of life kind of stuff, metaphysics. So it's very interesting to see him in this. It's very cool. These dang philosophers, man, they're all over the place. But he created the nebular theory, which says that our sun and planets form together from a rotating cloud of interstellar gas and dust called the solar nebula. So that solar nebula of gas and dust condensed into the sun with a rotating disk of gas and dust around it. And then that rotating disk of gas and dust formed the planets, moons, and other solar system objects. In the solar system, the sun is more than 99% of the mass of the solar system. And it creates the gravitational force that keeps planets in orbit around it and other objects as well, all the way out to the Oort cloud. And the surface gravity of the sun is 28 times that of Earth's, which doesn't sound like a lot, but it's a magnitudinal change, right? It's very, very much a lot. 70 chemical elements have been identified in the sun's spectrum, which we talked about in the emission and absorption spectrum section. The sun's outer layers likely have the same composition that the sun had at birth, which is about 71% hydrogen, 27% helium, and 2% other stuff, I believe, like lithium and beryllium. But over time, due to nuclear fusion, the sun's core has likely changed a lot of that hydrogen into helium, right, to about 38% helium. Okay. So now let's talk about the other different kind of things the sun does rather than just be the sun. We'll start with sunspots, right? So sunspots are dark, cool blotches that temporarily exist on the photosphere. Let's see if we can get a picture of that. So you can kind of see an image of it here, right here, or a rendition of it, right? That's a sunspot, right? They usually appear in groups of 2 or more, and when they almost always appear at least in 2s because they occur in opposite magnetic polarities, and oftentimes are also connected by magnetic field lines. And does that mean they appear on opposite sides of the sun? I don't believe so. I believe they're near each other. It's just that they have opposite magnetic polarity. Sunspots can last a few hours. They can last a few months as well. The largest sunspots are going to be visible at sunrise or sunset if you are able to glimpse the sun then. A typical sunspot is actually twice the size of Earth, which is insane. And the largest one can get up to 10 times the size of Earth, the diameter of Earth, I should say. The first observations of sunspots were recorded in China before 800 BCE, which actually clicks along with the lines that if you can see it at sunrise or sunset, right, it's probably a good chance of just quite early on in astronomical history. Galileo made the first telescopic observations of sunspots in 1610, and he also then correctly concluded that the rotation of the sun will transport sunspots across its surface. Sunspots are actually brighter than many cooler stars, despite the fact that it appears like a dark spot on the sun. And that's because the sun's apparent magnitude is so large, right, that something that is darker than the apparent magnitude of the sun is still going to be quite light. So yeah, it's only dark in comparison to the photosphere. Temperature of a sunspot is 4,200 Kelvin in the center of the sunspots, which the center of a sunspot is known as the umbra. And then the penumbra, which is the kind of outer gray portion of a sunspot, is a few hundred degrees cooler than the photosphere, right? So at any one time, there could be 300 sunspots that appear on the sun's disk. But this, it's not a pattern per se, but the increasing amount of sunspots and decreasing amount of sunspots is on a cycle known as the sunspot cycle, which lasts about 11 years. And the sunspot cycle coincides with the solar activity cycle as well, which is why astronomers and meteorologists actually do care about the sunspot cycle and they care about the solar activity cycle, which is why they care about the sunspot cycle, because the sunspot cycle is one of our best ways to gauge the solar activity cycle. In this solar activity cycle, the sun is most active for about 4.8 years, and over that time, over those 4.8 years, sunspots grow in number, and they become increasingly numerous. And then it also has the greatest outburst of energy and radiation. And then after the maximum, the sunspots decrease for about 6.2 years to a sunspot minimum, which I think can be around 0. I don't know if it's exactly 0. But the most recent solar activity cycle began in 2008, known as solar cycle 24, which makes me think we're actually it's 2020. So I think we're in solar cycle 25, quite possibly. But it's at the time that this was written, right, it wasn't necessarily the case. All right, so we got our other solar activity. We got solar flares, solar prominences, and coronal mass ejections. And what all of these are the eruptions of energetic particles on the photosphere. And again, this is mostly due to the active periods of the solar cycle. And locations where these eruptions of energetic particles take place are known as active regions. The first one they want to talk about is solar prominences, where fiery arches of ionized gas that move upward through the corona. Let's take a look at one of those, or a fake one. Here you can see an example of a prominence, right? So it's almost like, I think it's those things where it's like it looks like it's shooting out like gas and stuff. It's cool. And so usually this is due to the magnetic field of the sun. I guess just the way the magnetic fields are affecting the energy that's going through the sun. A typical solar prominence can span 100,000 kilometers, which is 10 times Earth's diameter, and can last for days or weeks. That's insane. The sun is terrifying. A solar flare is a sudden explosive outburst of radiation that goes across all parts of the electromagnetic spectrum, from radio waves all the way up to gamma rays. And we see this is the release of high velocity particles. And a single solar flare can release as much energy as Earth uses in 100,000 years. Let's see if we can find a picture. Do we have solar flares on this picture? We do not. I need to find a solar flare. Let me see if I can find one real quick. Maybe not TN's move, the solar flare, although it is cool. I wish TN was a better character, or like a fighter, I should say. So here's a solar flare. I don't know if this is a real solar flare or a just like a representation of a solar flare, right? But we can kind of see it occurring there. Let me see if I can get a better picture here. So it's kind of just shooting out a bunch of energy into space, right? Terrifying. They're very short-lived. They last for only a few minutes, and the longest only lasts a few hours. Much like solar prominences, tends to be energized by strong local magnetic fields. And usually solar flares occur right after the most energetic of all solar eruptions, which is a coronal mass ejection. Which takes plasma from the corona and blasts it out into space. And if you guys don't remember, the plasma is the gas of ions that we've talked about in the previous section. Is this a real coronal mass ejection? That'd be wild. It is. This is from 2000. This is a coronal mass ejection. This is blocking out the light of the sun to kind of give a better look at the mass ejection. That is awesome. But that's all they talk about with coronal mass ejection, so that's fun. So the radiation that the sun emits reaches Earth in 8.3 minutes. And the electromagnetic radiation the sun tends to emit is in the upper levels, the gamma rays, X-rays, UV rays, and then visible radiation. Particles released during solar flares will arrive a few hours or days later after the solar flare. And so this sounds dangerous, but the magnetic fields of Earth shield us from from the particles from solar flares. But if you're not necessarily within the magnetic field or all the way within the magnetic field, it can be very hazardous, which means it's hazardous at high altitude. So airplane passengers, astronauts, and spacecraft electronics are all at the whims of solar flares to an extent, not totally, obviously. And electrically charged particles from the sun can also excite atmospheric atoms and ions to very high energy levels, right? And so then when those atoms and ions are then going back down energy levels after being excited by the sun's particles, the de-excitation, that is when we see things like the aurora borealis and aurora australis, also known as the northern and southern lights. So oxygen will emit a pale green color. Nitrogen molecules produce a red-violet light, and nitrogen ions will emit blue-violet light as they are releasing energy from the excitation, right? So during the de-excitation. Okay. The northern and southern lights are visible in the Arctic and Antarctic regions. However, after a solar flare, about 2 days afterwards, you can sometimes see them in latitudes in between, or the middle latitudes. Auroras themselves will reach a peak 2 years after a sunspot maximum. I guess that's when the atoms and ions are finally releasing that energy, right? Um, Electrically charged solar particles can disturb Earth's magnetic field and interfere with compasses and magnetic instruments. And on top of this, these strong particle storms have resulted in things like surges in electric power and telephone lines, and blackouts and disruptions of radio transmissions and navigation signals. And in the case of radio transmissions and navigation signals, the way that it disrupts it is by increasing the ionization in the atmosphere, or the magnetosphere. Don't ask me how this all works. I don't know. But due to the impact of solar flares, the NOAA, the National Oceanic and Atmospheric Association, monitors magnetic field and activity daily and will issue space weather alerts, warnings, and forecasts. If that's not the most cyberpunk sentence in this whole resource or this whole year, it's great. Space weather alerts. Solar flare radiation can't heat the upper atmosphere, which causes it to expand. Which then, when the atmosphere expands, it increases the effects of friction and drag, friction and drag on spacecraft and satellites in low Earth orbits, right? So if they're orbiting Earth pretty close to Earth, right, they're outside the atmosphere, but with this solar flare causing the atmosphere to expand, right, then the drag of the atmosphere is reaching a place it wasn't supposed to, which causes satellites to plunge from orbit and then be destroyed on re-entry. And the example they bring up is Skylab, the U.S.'s first space station, which I think there's a space race section on later. It is the U.S. first space station, and its orbit decayed too fast due to increased drag, so they couldn't necessarily calculate like what was going to happen to it, or like the calculations they had were all of a sudden nullified by the expansion of the atmosphere. So Skylab plummets to Earth in 1979. Solar wind, last section of here. Solar wind is a stream of energetic and electrically charged particles that flows outward from the sun at all times. It is much faster, much thinner, and hotter than any wind on Earth, and it's detectable by instruments on spacecraft. And in fact, near Earth, the average solar wind is 450 kilometers a second, which is very fast, 1 million miles an hour. But we are protected from it by the atmosphere and magnetic fields. And in a shocking turn of events, solar wind is most active, most intense when solar activity is also at its maximum. And so we see the large emissions of solar winds occur most often during coronal mass ejections, creating pretty insane auras. And solar wind itself mostly comes from coronal holes, which is regions in the sun's corona where gases have a lower density than their neighboring areas. And so the reason the gases have lower density is because the magnetic fields are relatively weak, which means that it's not keeping in that energy, which allows high-speed solar wind streams to escape. And that is the sun. A lot going on with the sun, a lot more than you realize. But in the next section, we're finally going to get into stars, which is one of my favorite sections. But until that next video, thank you guys so much for watching. I'll see you